We will now go on to study the concept of ionization energy. If an atom or an ion of an element is in its gaseous state and is given enough energy, one of its outermost electrons may be knocked out of its orbit. This minimum amount of energy that is required to do this is called the ionization energy. And this can be represented using the element iron in this example here. Here we're seeing an atom of gaseous iron, and if given enough energy, called the first ionization energy, IE1, it produces an ion of iron 1, and an electron is knocked off here. This one can further be ionized, so it becomes a gaseous ion. Given enough energy called ionization 2, IE2, it produces Fe2 ion, gaseous ion, and an electron is given off. There can be a third and fourth and fifth ionization also. The following table here shows the trends in ionization energy for some elements. This group here shows IE1, IE2, IE3, IE4, IE5, IE6, IE7, IE8. Now you'll see what it is for various elements, some of these ionization energies. So we look at the element hydrogen. Hydrogen has only one electron, so knocking off that one electron requires an ionization energy of 1,312. Helium, with 2, has a relatively high ionization energy for the first one, and then the second electron requires that. Lithium, to knock this one out, so always the first ionization energy is used to knock off electrons from the outer shell, then you go into the inner shells, right? So in this case, lithium has 1 electron, so that is the amount of energy required to ionize that. And then you go now and you're breaking this duplex here. It takes 7,298, and then the other one, the third one, 11,855. Beryllium, and you can read that here. You can read that out here, first, second. But look at the third. Third means you're breaking the duplex there. It's 14,849, and then to remove the fourth one, that is the amount of energy there. So look at these trends here. You can see that the 3 outer electrons here will take progressively higher and higher energy until you come to this one here, breaking that duplex here. Look, it jumps from 3,000 to 25,000. So it appears that as you try to break the duplex here, it takes a considerable amount of energy than to remove these outer 3 electrons here. Same thing is happening for all the other elements. Carbon, small, slightly higher, slightly higher, slightly higher. But look, 37,831. Nitrogen, smaller one, little bit bigger, little bit bigger, little bit bigger, little bit, 53,000. Why? Because when you reach down there, it's difficult to remove an electron from the duplex there. Same thing is happening in all of these here. When you come to neon now, same thing here. You're getting all these. Sodium. Now this is slightly different from those because you're having 3 shells here. Look, to take this one electron off, you need that amount of energy. Now when you try to remove an electron from this octet here, it takes 4,000 here. And then of course, it gets bigger and bigger and bigger. Same thing here, magnesium, a small one here, relatively higher one, and then a huge one here. So apparently, what we are seeing here, to remove the outer electrons takes relatively smaller amount of energy than that what is required to break the duplex or the octet. And these ionization energy patterns can help us to know how many valence electrons there are in atoms of elements. Let's go on now and see why that was so. Let's analyze some of these results here. Let's look at what is it here for lithium and why that is so. See, lithium has a forced ionization energy of 497 kilojoules per mole. It has only one valence electron, and that is the amount of energy that's required to remove that one mole of valence electron. Now we can remove that electron there. So what is happening now is that that shell there is absent. Delete this guy. Yeah. So we don't have a shell anymore there. I see now these two electrons here, this duplex here, are very, very close to the nucleus. And that's why now to remove this second electron, it requires that amount of energy. If you look at ionization energy pattern, and you discover that you're using only a relatively small amount of energy for the first ionization, and then all of a sudden you encounter a huge ionization energy for the second one, it means that that atom there has one valence electron in its outer shell. Look at this one here for beryllium. There's beryllium here. Now you can see beryllium here has a first ionization energy and a second one here. Question might be asked is, why is it that these two electrons, which are found in the second shell, are at equidistant from the nucleus? Why is it that this one here is higher than that one? It should be the same, because look, the force with which the nucleus is attracting these electrons there is the same. The answer has to do with something that is called electron-electron repulsion. You see, when these two electrons are here, they're mutually repelling each other. So if this one is pushing that one, this one of them just needs a little nudge to knock it off. So this is the one here. So if we take that one off there, now this one has no electron-electron repulsion. There's nothing pushing this one here. That one was pushing it. That is why that was. So now you need more energy to knock this one out because of the absence of that electron. And that's why this one will be slightly higher. Now we encountered this big one here. Why that is so? Is because now that shell is gone, and these two here represent the duplex, and is very, very close to the nucleus. And to move this electron away, you need that amount of energy. So what's the trend? If an element has two valence electrons, this is how you'll know. The first ionization will be small, the second one slightly higher, but the third one will be much greater than that. And in this case, it's 14. So that's the trend there. No, look at the other one. Let's look at another one. One that has 3 electrons. Let's look at boron, for example. Boron has these ionization energy. Small one here, the second one is here, third one is here, and the fourth one, look, big jump between 3,000 and 25,000. Reason for that, similar to what we've been talking about. You have 3 electrons here repelling each other, and because of that, this first one is like that. So it's not too big. So if you remove this guy here, now what we have? We only have 2 valence electrons remaining there. And now you're going to have 2 of these repelling each other, right? But it will still be higher than that, because in this case, 3 of them are repelling each other. So this one here is slightly bigger than that. Remove that guy there. Remove this one here. We only have 1 valence electron now, and therefore nothing to repel it. It's taking a high ionization energy than that one there. Remove this one, okay? And then you remove the shell here. Now you're left with the core electrons here. This is a duplex. And to remove that, you need all of that energy. Someone might want to ask, why is it that this is 25 for boron, and why this one is 14 for beryllium? Note that the nuclear charge on boron is greater than that for beryllium, and therefore the nucleus here will be holding on to these electrons stronger. And the same concept can be used to explain the 4 ionization energy for carbon. You have 4 electrons there. 4 of them are repelling each other. This one is small. Remove that one there. 3 left. This one here, bigger than that one because of these 3 only. Another one, these 2 repelling each other. That one there, gone. This one goes. That one goes. These are the 4 ionization energy. And of course now, You remove that guy there. And good. This is the fifth one. See? Greater nuclear charge than all of them there. So this is the pattern of ionization energy with respect to the number of valence electrons and the core electrons. Now we're going to look at ionization energy, atomic radius, and ionic radius. We do it when positively charged ions are formed. Here's an atom of sodium. It has 1 valence electrons. So here is first ionization energy, and then you end up with a positively charged ion. Notice that it uses that amount of energy, okay? And now that shell is gone. So notice how the ionic radius becomes smaller. So the ionic radius is always, for positive ions, smaller than the atomic radius. Why? That entire shell has disappeared. There's no electron inside there anymore. We can continue with this guy. We can now try to remove an electron from the sodium ion. Now that this is now an octet, and these are very much closer to the nucleus than that one there. And to break the octet, you need a larger amount of energy here than that there. So it follows the pattern I talk about. First ionization energy is small, followed by a huge one that indicates you're coming to breaking an octet or a duplex. And again, if you remove one of these, because of less electron repulsion, becomes 2 positive here, and you can see this shell here is smaller than this one here, so there's less electron to repel each other there. Anytime you remove an electron from an ion or an atom, the resulting ion becomes smaller than what it was before. The factor of electron-electron repulsion. We've spoken about that before. This is magnesium here, and its first ionization energy is this. See? 1 electron becomes Mg+, and look, 1 electron is left now. And also note how this ion becomes slightly smaller than 1. We can go on now and do the second ionization energy. Look, to remove the one now, see, watch. It's bigger than is 14. This was only 738, and now this one is 1450. All because there's less electron repulsion, and you get this. Note again how this shell disappears, and the radius of the Ng2 plus ion is smaller than that of the one before. Again, you can try to break the octet there, and you use a huge amount of energy. So here's the pattern again. If you have 2 valence electrons, you see 2 ionization energy. One is small and the other one is slightly bigger. And then the third one that is huge, which is indicative of breaking the octet or the duplex. Negative ions. This is a chlorine atom here. You can see chlorine has 7 electrons outside. It loves to have the octet. So you can gain 1 electron here, and energy is produced in this case. See, it becomes a chloride ion, a big, huge ion here. Why? This electron that goes in causes more electron repulsion, and that's why it's bigger now. So note that whenever an atom absorbs an electron, the ion that is formed is always bigger than the atom that was present there before. So here's some summaries here. As an atom loses an electron, it forms an ion whose radius is smaller than its atomic radius. An example of this is magnesium, atom losing 2 electrons. If the atom loses an entire shell, it's very much smaller than its atomic radius. When an atom or ion gains an electron, the radius of the resulting species is much larger than that of what it had before. Trans-Dunga group now. We'll use lithium, sodium, and potassium here, group 1A, to tell you about the trans-Dunga group. Now you can see here, this is the atomic radius of lithium. Lithium has 1 electron outside here, and it has a nuclear charge of 3+. Sodium now has 3 electron shells. An inner one here, a second one here, and a third one here. But it has a nuclear charge of 11 positive. Now, there are two things that are operating here, the interplay of two things that will affect the radius of an atom. One is the effective nuclear charge, and secondly is the number of electron shells. Two things will help to increase the radius of the atom: the number of electron shells that are present, and also the number of intervening shells that shield the outer electron shell from the positive influence of the nucleus. So in this case, this outer electron for sodium is being shielded by these two inner core electron shells. So these 11 positive charges here do not have that strong influence on this outer shell here. When a shell is added, the radius of the atom increases exponentially, far more than the contraction due to the increase in nuclear charge. So as you go down the group here, the inclusion of an extra shell here overwhelms the decrease that is caused by the increase in nuclear charges here. Same thing happens here. This outer electron shell is being shielded, or electrons here are being shielded by 1, 2, 3 shells now. So the positive nucleus is not really having that strong influence on these one here. Apart from that, also the shells, when they add another shell here, it expands exponentially. That is why, therefore, in spite of the fact that as you go down, the nuclear charges increase, the radius keeps increasing because of the addition of these extra electronic shells here that gives an exponential increase. Now you can see what's happening here. These are in the same period of the periodic table. As you move towards the right here, even though there are only 2 electron shells here, same thing, because of this high nuclear charge here from fluorine here, is able to pull in this shell here more than lithium does to its own shell. Same thing happens in this case here. These have the same number of electron shells. This one here, same number of electron shells shielding the nucleus, same number of electron shells shielding the nucleus here. But because of this huge nuclear charge here, the bromine nucleus is able to pull in all these electron shells closer to itself. That is why now you find as you move across, we've spoken about that already, the atomic radius decreases from left to right of the period. So this is how trends happen down a group. Two things are operating. As you go down a group, the number of electron shells increase, and that causes an overwhelming increase in the atomic radii, even though the nuclear charge increases. So I hope you've learned from that, and that is what it is for ionization energy and trends in ionization energy in these various groups. So once again, thank you for listening.